All right, so now we're going to talk about, well, we're going to sort of like first be introduced to this concept of Lewis structures or electron dot structures. Those two names are synonymous. I actually like this part of general chemistry a lot. It's where you start connecting atoms together and learning how they're connected. We got to learn a few skills before we get to where we can just draw the structure of anything. So we're going to take this like one step at a time here. First of all, let's discuss why atoms form into molecules, right? We have all these individual elements that we see from the periodic table. Why do they bother bonding to one another anyway, right? So it all relates back to this concept of the octet rule. And we first were introduced to this concept when we were talking about which elements form which ions. So let's remember that we did this just by looking at the periodic table. So for example, chlorine, we know has 1, 2, 3, 4, 5, 6, 7 valence electrons, which means it likes to accept an electron to form a chloride ion, right? And we knew all that just by looking at the periodic table. And the whole idea was it has 7 electrons, it wants to get to 8, thus it will accept an electron and have that -1 charge, right? So remember, hopefully everybody has this down from the previous set of chapters where just by looking at the periodic table, we know what type of ion chlorine likes to form, right? How many valence electrons it has, how many it needs to complete its octet. So it turns out that the logic is the exact same for covalent bonding as well, right? So again, we're talking about covalent bonds. We're not talking about the chloride ion. We're talking about chlorine in a covalent bond where it's sharing electrons. But it turns out that it does it for the same reasons, right? So two chlorine atoms, if we drew their Lewis dot structure, remember we learned how to do that, and that was just putting the number of dots that correspond to the number of valence electrons on an atom. So by looking at where chlorine was on the periodic table, we knew it had 7 valence electrons, so we can build its electron dot structure. 1, 2, 3, 4, 3, 4, 5, 6, 7, right? Okay, so we can use the Lewis structure of the chlorine atom to understand why chlorine likes to form a Cl2 molecule, where 2 chlorine atoms are actually bound to one another. And the reason is because you have these 2 chlorine atoms, each with 7 valence electrons each. Well, when they come into close contact with one another, they can share a pair of electrons, i.e. form a covalent bond, where now they get to both count that pair of electrons into their octet rule, right? So one chlorine has 2, 4, 6, 8, gets to count both those electrons. So its octet is satisfied. The other chlorine atom, 2, 4, 6, 8, it gets to count that same pair of electrons. So its octet is satisfied, right? So again, we can sort of understand why these 2 chlorine atoms will form a covalent bond with one another. And it's because they both want to satisfy their octet. And by sharing that pair of electrons, they do. Okay, so again, just to kind of illustrate here, the left chlorine atom will count all those pairs of electrons. Again, they're sharing now this pair of electrons here. So the chlorine in blue gets to count all 8 of those electrons towards its octet. The chlorine in pink gets to count all 8 of those electrons towards its octet. Okay, so the name of the game is going to be to get to where we're drawing structures like these Lewis structures here. And these show how atoms are connected to one another, right? So how many electrons are being shared, how many electrons aren't being shared. And so let's just take a look at one of these real quick. First of all, it bothers me that that's touching. All right. This would be our molecule here, H2O, water. And here would be what we call our Lewis structure. And again, it shows who's bonded to who. So we see that the oxygen is bound to 2 hydrogens, right? So H2O is not HHO. You have the oxygen in the middle, and it's got a single bond to each hydrogen, okay? We can see that there are these dots around the oxygen atom. These are called lone pairs. These are non-bonding electrons. Okay, so each atom is going to have a collection of bonding electrons and non-bonding electrons. Maybe all the electrons are bonding, maybe all of them are non-bonding, but nonetheless, there could be a mixture. The non-bonding electrons, the lone pairs, are represented as dots, and you'll always see 2 of them together because, again, they're lone pairs. So each dot represents an electron. They're always in pairs, so again, we call them lone pairs. They're not participating in bonding. The lines represent the covalent bonds. They represent the sharing of electrons between, in this case, the oxygen atom and the hydrogen atom. Okay. So in our Lewis dot structures, importantly, just to pick the anatomy apart, we have lone pairs on our atoms, as well as covalent bonds between atoms. Notice we're using that symbol for each one. So the O is oxygen, the H is hydrogen, et cetera, et cetera. Okay. Importantly, we need to be able to count the electrons that we see in a given Lewis dot structure. Again, this is just going to bug me. Okay. Each covalent bond represents 2 electrons. Okay, that's that sharing pair of electrons that we saw in that chlorine molecule. So this represents 2 electrons and this represents 2 electrons. So that means that in our covalent bonds in this structure, we have a total of 4 electrons, again, in covalent bonds. Each lone pair, within a lone pair, each dot represents a single electron. So each lone pair then represents 2 electrons. So this would be 2 electrons here, and this would be 2 electrons here. So in this particular structure of water, we have 4 electrons in lone pairs. Okay, this is important because we're going to need to, basically, you're going to be drawing these structures, right? So you want to be able to draw a structure, look at it, and be able to tell how many electrons you have put down. You'll hear me say this phrase a million times. How many electrons are on the board? Meaning, like, how many have been drawn on that structure? In this case, we have 4 in a electrons in covalent bonds, and 4 electrons in lone pairs. Okay, let's remind everybody again how we figure out how many valence electrons a particular element has, right? So in water is hydrogen and oxygen. Remember, hydrogen has 1, 2, then you skip 3, 4, 5, 6, 7, 8. So the oxygen atom has 8 valent, oxygen atom has 6 valence electrons. The hydrogen atom has 2 valence electrons, right? And that's how many electrons they're like bringing to the table. So for example, when we're forming a water molecule, we have our hydrogen that has 1 valence electron. We have 2 of them. And an oxygen that has 6 valence electrons. Again, I just figured that out by counting 1, 2, skip 3, 4, 5, 6. And so we can calculate the total number of valence electrons just given this molecular formula here, right? Given H2O, we can figure out that that's 2 valence electrons from hydrogen and 6 valence electrons from oxygen. Again, it's 2 valence electrons from hydrogen because hydrogen's got 1, but there's 2 hydrogens in that molecule. So that brings us to a total of 8 valence electrons total. Okay. okay? This is the skill that we need. We need to be able to both count by looking at the Lewis dot structure. We also need to be able to calculate it based on just the molecular formula, because that's going to be the goal, is to go from molecular formula to Lewis dot structure and eventually to the actual 3D geometry of the any particular compound. Okay, so for water, we say it has 8 valence electrons total. What about nitrogen trifluoride? So let me get rid of this, and I'll fill out. So 1, 2, 3, 4, 5, 6, 7, 8. Nitrogen trifluoride. Okay, so nitrogen has 5 plus 3 times the 7 on the fluorine, right? So the total number of valence electrons within this molecule would be 26. Okay, and that means that when you draw your Lewis structure of nitrogen trifluoride, it should have 26 electrons. And we're going to build up to that. We don't know how to do that quite yet, but that's where we're going with this. That's why we need to know how to do this. Okay, now let's do an ion, the nitrate ion. This is going to make it a little bit more tricky. We have, again, our nitrogen. It's not fluorine. Oxygen. So nitrogen, we have 1 nitrogen, which has 5 valence electrons, plus 3 oxygens, which have 6 valence electrons. And then we're going to add, because the nitrate ion has that -1 charge, that means that we need to add 1 more electron, right? If we think back to what that -1 charge meant, it meant that there was 1 more electron than, you know, those atoms started out with, right? So we have to add that 1 on there. So mental mass is 23, 24. So that means this particular molecule would have 24 valence electrons. Okay. In terms of a full valence shell, so the other thing that we're going to want to see, we want to be able to do when we look at our Lewis dot structure, is be convinced that each atom indeed has a full valence shell. Let's actually do it here. This was the Lewis dot structure I gave you for water, okay? We need to make sure that all the atoms within this structure have a full valence shell, or a full octet. The weird ones are these elements that are kind of have this exception to the valence rule, meaning they don't have quite as many electrons that they need to be a complete octet. Hydrogen is really the one that you guys got to remember. Hydrogen only, it's so tiny, right? It's just the first element on the periodic table. It can only fit 2 electrons into its octet, right? It's fully satisfied when it has 2 electrons. Another one is helium, which you don't have to know at all because it doesn't form any compounds with anything. The other weird ones are beryllium, which has an exception to the octet rule where it only needs 4 electrons. Again, it's because it's kind of tiny. And boron, same idea, it's kind of tiny. So it only needs 6 electrons to have a complete octet. Okay, so then looking at this water, so oxygen, importantly, is not an exception. So it's going to want 8 electrons in its valence shell. So when we look at our structure for water, we should be able to count 8 electrons in oxygen's valence. So first of all, we have 4 that come from the lone pairs, and then we get to count these covalent bonds in its valence as well. So indeed, oxygen has 8 valence electrons in this structure. Hydrogen only needs 2, and it gets those 2 from this bond right here, right? So a single bonded hydrogen, which is always what you're going to see, is a hydrogen with a single bond, because that means that that hydrogen has 2 valence electrons. Okay, so each of my hydrogens, just to be good, I'll sort of show here. this hydrogen has this pair of electrons, right? So importantly, when you're drawing your Lewis structure, you know if it's correct because each atom's valence is satisfied. Each atom's octet rule is satisfied. And again, the important one to see here, maybe I'll even get rid of some of these markings, is the oxygen has its 8, the hydrogen has its 2, and this hydrogen has its 2, right? And again, both atoms get to count the ones that are involved in the covalent bond. A lone pair only applies to oxygen, but if it's a covalent bond, both atoms get to count that. All right, so let's go ahead and convince ourselves of 2 things here. Again, this is going to drive me nuts. Let me just... One, let's practice counting valence electrons within the structure, right? So for both of these, we knew based on the formula how many it should have. Let's make sure that when we look at these structures, we can convince ourselves that that's the case, okay? We kind of just did it for water, so let's focus on the nitrogen trifluoride here. So again, in terms of counting electrons, each lone pair counts as 2. So this is 2, 4, 6, and then the lone pairs, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. So I got 26 valence electrons based on that Lewis dot structure. And again, one of the things that we'll be aiming for, and again, we're not quite here yet, we're just counting at this point, but you can see how it matches the number of valence electrons for the formula. So if I were drawing this formula from, or this Lewis dot structure from scratch, one way that I would double check that I actually got the correct result is the fact that this number matches the number that I get just from looking at the molecular formula. The other thing I want to do is to make sure that each atom has its complete octet, right? And so for the case of water, we said hydrogen's an exception, it only needs 2. For the case of our nitrogen trifluoride, none of those are the exception, right? So both the nitrogen should have its full octet, and every single fluorine should also have a full octet of 8 electrons. And so indeed, this fluorine here has 2, 4, 6, 8. You can see due to symmetry, it's going to be the same for all the fluorines, 2, 4, 6, 8. 2, 4, 6, 8. And then for the nitrogen, it has a full octet. It's got many shared pairs of electrons, right? So pay attention to my color coding in terms of how I'm calculating it. 2 in lone pairs, then 4, 6, 8. Right, so it's got those 3 covalent bonds. It gets to count 2 electrons for each of them, and then that lone pair. So we know how to verify not only the number of valence electrons we got, check. We also can verify our octet rule is satisfied. We don't really know how to draw these structures yet. I want to make that clear. I don't want anybody to freak out like I didn't know that that was the Lewis dot structure for nitrogen trifluoride. You wouldn't, okay? We're not quite there yet, but importantly, we have this skill of counting electrons, and we have the skill of making sure that each atom within a valence or within a Lewis dot structure has a complete octet. Last thing we want to talk about is this idea of bond order. Okay, so up until now, we've been sort of seeing exclusively single bonds, which is the sharing of 2 electrons. Like would be the case as we saw with chlorine, Cl2, also with fluorine, F2. There's this single bond, and then, oh look, we can even verify that everybody's got their full octet, 2, 4, 6, 8. Same with this guy over here, 2, 4, 6, 8. Okay, so that's a single bonded fluorine where they're sharing 2 electrons. There are other bond orders. There's a double bond as well as a triple bond. In a double bond, 4 electrons are being shared. Okay, so that's what this represents here. Each line still represents 2 electrons being shared. There's 2 of them, so that represents 4 electrons are being shared. Likewise, in a triple bond, you see these 3 lines. That represents that 6 electrons are being shared. We can still verify that everybody's got a complete octet here. And that might not be a bad idea for you guys to go and do on your own. One thing to note about single versus double versus triple bonds is just the relationship to bond length and bond strength. So really, let's focus on these top 3 right now. So these are all carbon-carbon bonds. Carbon-carbon single bond versus a carbon-carbon double bond versus a carbon-carbon triple bond. We see that as the bond order increases, bond length decreases, right? So single bonds are the longest, double bonds are a little bit shorter, triple bonds are even shorter than that. Not only that, but the amount of energy required to break those bonds increases with bond order, right? So it's harder, or it's easiest to break a single bond, harder to break a double bond, even harder to break a triple bond. And we see that regardless of who's bonded to who, right? So if we look at carbon-carbon double triple bonds versus carbon-oxygen single double triple bonds versus nitrogen single double triple bonds, we see the same trends in all of them. As bond order increases, bond length decreases, but bond strength increases.